Next talk will be given by Jack Wilson on fundamental physics with high heritage neutron sensors on the lunar surface.
Okay, very good. Right, so yeah, a slight change of gear here. I'm going to talk about general relativity and talk about particle physics instead. Yeah. So this talk is going to be about measuring the neutron lifetime from the surface of the moon using a neutron detector that has or at least could have a lot of heritage from Messenger and Psyche NS. So I'll start with a bit of motivation, because I suspect that many of you are not familiar with the neutron lifetime puzzle. So, as I expect you know, neutrons inside nuclei can be stable, but free neutrons decay via beta decay with a mean lifetime of around 880 seconds. And this is a very important decay because it's essentially the cleanest example that we have of the weak interaction. The precise value of the neutron lifetime also has important implications in fundamental physics and cosmology, but it turns out that it's very difficult to measure, and I'll explain why. So if you go to the next slide. Right, so the neutron lifetime is important in fundamental physics because it can be used to measure the magnitude of VUD, which is one of the elements of the CKM matrix. And the CKM matrix describes the relationship between the mass and weak eigenstates of quarks. And checking the unitarity of the CKM matrix is one of the strongest constraints we have on the completeness of the standard model. So if there are only 3 generations of matter, then the CKM matrix must be unitary. But if there are more generations that we haven't yet discovered, then the CKM matrix wouldn't be unitary. And right now, the strongest test we have of the unitarity of the matrix is from the first row, which includes VUD. And in fact, what we find is that there's 3 sigma tension from unitarity. So what this indicates is that we need a reliable and precise measurement of the neutron lifetime to feed into VUD. The lifetime is also important in cosmology, in calculations of primordial nucleosynthesis. So the reason there is that in the very early universe, the ratio of neutrons to protons is 1 to 1, because the reaction that's shown on the left can proceed either forwards or backwards. But as the universe expands and cools, the backward chain becomes unfavorable, and the ratio of protons to neutrons decreases to about 1/6. Then, in the next 20 minutes, nucleosynthesis occurs. So essentially, the protons and neutrons are bound together. Almost all of the neutrons end up inside helium-4. But of course, during that 20-minute window, the free neutrons decay. So the ratio of hydrogen to helium that you end up with is determined by the neutron lifetime. And in fact, the uncertainty on calculations of primordial helium abundances right now are dominated by the uncertainties on the neutron lifetime. So that's why it's interesting. Why is it difficult? If you go to the next slide. So there are 2 well-established and reasonably high precision ways of measuring the neutron lifetime. The first is called the bottle method, and it involves storing ultra-cold neutrons and then periodically measuring how many survive in order to plot out the decay curve and calculate the neutron lifetime. The state-of-the-art measurement is UCN tau at Los Alamos, and it reports both statistical and systematic uncertainties less than 0.3 of a second. The other technique is the beam measurement, and that involves passing a cold neutron beam through a volume in which the protons that are produced are trapped. And then by measuring the rate of production of protons and the absolute fluence of the neutron beam, you can calculate the lifetime. Okay, so that's all well and good. We've got 2 measurements. What's the problem? If you go on to the next slide. This figure isn't displaying properly, but there should. What's happening here is that, well, this isn't. Anyway. The figure on the left, the red points show the recent beam measurements, and the blue points show recent bottle measurements. And since 2005, there's been a significant disagreement between the 2. And in fact, since June of this year, when a new bottle result was published, that disagreement has reached the 5 sigma level. And it's this disagreement that we call the neutron lifetime puzzle. So you can presumably see that this is a big problem in experimental nuclear physics. And the most reasonable explanation for this discrepancy is that one or potentially both of these classes of experiments contains a systematic error that hasn't been assessed properly. But it's also possible that the neutron is doing something strange, and that 1% of the time when it decays to a final state that doesn't involve a proton. So people have hypothesized that it could decay to dark matter particles, although there are strong astrophysical constraints on that. It remains a possibility. So what's needed here, we suggest, is a third measurement technique with completely independent systematics that could break the existing stalemate. And what we're proposing is that technique could make use of planetary neutrons with a landed lunar detector. So if you go to the next slide. Right, the reason that the moon gives off neutrons is that the lunar regolith is bombarded with galactic cosmic rays. They collide with nuclei in the soil and release large numbers of high-energy neutrons. Those neutrons then have their energies moderated downwards, and some fraction escape from the surface. And the important point is that the energy distribution of the neutrons that escape is characteristic of the elemental makeup of the regolith, or planet soils. And for that reason, several planetary science missions have flown neutron spectrometers. If you go to the next slide. So the figure on the left here shows some simulated spectrum for the neutron flux emerging from Venus, the Earth, and the Moon, where the Highlands and the Maria have been separated for the Moon. The reason for that is that the Maria contain several neutron-absorbing elements in high abundances, and that reduces the low-energy thermal neutron flux. It's this low-energy thermal neutron flux that's important for measuring the neutron lifetime. And the reason for that is that the velocities of those neutrons are typically a few kilometers per second. So the time of flight from the surface to a spacecraft that's a few hundred or a few thousand kilometers above the surface is of order the neutron lifetime. Also, all of the thermal neutrons on Venus and the Earth and the low-energy thermals on the Moon are gravitationally bound. And the time of flight surface to surface for a gravitationally bound neutron is also typically of order the neutron lifetime. So what this means is that you can make inferences about what the neutron lifetime is by looking at how the neutron flux changes as you move away from a planet, or by comparing the thermal neutron flux leaving a planet to that returning. Next slide. So given that there are data out there, we thought we'd put this idea to the test. And we've looked at some data taken by Messenger's neutron spectrometer during the spacecraft's flyby of Venus, and the Lunar Prospector neutron spectrometer during its initial highly elliptical orbits. The measurement principle is illustrated with the figure on the left. So essentially what you do is you simulate the production, transport, and detection of neutrons, and then compare that to measurements. Next slide. So this, again, this should have some uncertainty regions highlighted, but the transparency's disappeared here. But what this figure does is it shows the measurements that we made using existing data in comparison to existing laboratory measurements. And what you can see is that the uncertainties are somewhat large, and that's to be expected. We have a small amount of data that we were constrained to use, around 45 minutes for Messenger and 2 days for Lunar Prospector. And of course, the instruments were designed to do planetary science, not nuclear physics. But nonetheless, these measurements do act as a proof principle. It demonstrates that the neutron lifetime can be measured using planetary neutrons. And in fact, we can make a much better measurement, we think, with a landed lunar detector that's designed to make this measurement. Next slide. So the principle behind a lunar landed measurement is that you would measure the upward going thermal neutron flux and compare that to the number of neutrons that return on bound orbits. For a neutron with a given momentum, the probability that it survives its sort of round journey is a function only of the mass of the moon and the neutron, which is very well characterized.
5 minutes.
10 minutes.
Thank you. 5.
Next slide. Right, so this cartoon illustrates the sort of detector that would be required in order to measure the thermal neutron flux coming off the moon and returning on bound orbits. It could use exactly the same electronics as we used in Psyche's NS, and it would use very similar detector technology to Messenger's neutron spectrometer. The idea behind this design is to maximize the useful area by using flat lithium glass neutron sensors. We'd have two pairs of those, one looking down and one looking up. The reason you want them in pairs is that you're trying to measure the thermal neutron flux, and the sensors are sensitive to both thermal and higher energy epithermal neutrons. So you have to wrap one of the pair in cadmium in order to prevent the transmission of thermal neutrons, and then you get the thermal neutron count rate by looking at the difference between the two. Each of these pairs of sensors would be placed inside some neutron shielding material. Here we assume that would be boron-10 enriched boron carbide. And the purpose of that is to restrict the field of view of the detector, and also to prevent the passage of neutrons directly from the surface through the lower pair of detectors and into the upper pair. So this instrument would function anywhere on the lunar surface, but it would be ideally placed in the highlands because you get much better statistics there due to the higher thermal neutron count rate. It would also be advantageous if it could be placed on a region of the lunar surface that has relatively little composition variation, spatially on sort of kilometer scales. And that would be done in order to minimize the difference between the upward going and downward going flux that was caused by composition rather than life.
3 minutes.
Thank you. Next slide. Right, so the solid grey line in this figure here is a result of simulation, and what it shows is the expected statistical uncertainty on a lunar landed measurement of the neutron lifetime like the one that I just described. Also on this slide are the preliminary proof of principle measurements that we made and two additional curves showing the expected statistical uncertainties on orbital measurements. So you can see that the lunar orbital measurement gives slightly less good precision than the landed detector, and the reason for that is that the landed detector can very successfully isolate the upward going and downward going components, so it provides quite a clean measurement of the neutron lifetime. Next slide. Right, so the problem is that we have these two laboratory measurements that are quite precise, but they differ by nanoseconds. Yep. So in order to, the goal here would be to distinguish between the two. And the way, in order to do that, you need 3-second statistical precision from a landed measurement. And what you can see here is that you get that 3-second precision in 30 days of observation. So the instrument would have to survive the lunar night, but it wouldn't have to operate through the night. And the required observation time could be reduced simply by increasing the area of the detectors. So I think what this demonstrates is that a lunar landed measurement is a potential path to resolving the neutron lifetime anomaly, which is a long-standing problem in fundamental physics. Thank you.
Excellent. Thank you very much. Is this the last slide?
It is, yeah.
Excellent. Thank you very much. Are there any questions? Maybe I will ask, what is the power requirement on this instrument and how it should be coupled to the surface?
So we were imagining the placement requirements are very loose. It could be placed on essentially any lunar lander and it would work fine. I think Messenger's NS used about 3 watts, so this would be comparable to that in terms of power requirements.
And ideally, you would like to go through full lunar day several times at least, right? To cover entire, lunar day and night.
Well, the longer the better. The longer you're there, the more you improve the statistical precision. Yeah.
Excellent. Thank you very much.